Hello everyone, welcome to Practical Mechanics. I'm Mohsen. Today's video is about thin wall pressure vessel. We consider first a spherical pressure vessel, find out, derive its formula for thickness, and then in the next video we talk about cylindrical pressure vessels. We draw more circle for these pressure vessels. We have a look at ASME code for spherical pressure vessels, and then consider the effect of welding, mechanical allowance, corrosion allowance, erosion allowance, and milling tolerance for the plate. Let's start with the spherical shell. Thin walled spherical shell, thickness divided by outer diameter must be actually less than a value that the standard says, and if it is satisfied, the ratio is satisfied by code of a standard, it is called thin wall cylinder. Otherwise, pressure vessel is thick wall cylinder, and distribution of stress and formulation is completely different. Let's consider a thin wall cylinder. Thickness is called T. We consider the mean radius, average radius. We have our I, our O, and RM here, and later we will see that the standard use only outside diameter or outside radius, and we say why. Then, if I cut this spherical shape in any direction, doesn't matter, we have such actually shape, and this is a hemisphere. If we wanted to make it as a little more clarified, it's a hemispherical shape. The thickness of the edge that the stress is applied, because we cut it, the stress in the tensile stress in the direction of normal to the plane of the cut section. And all these stresses is due to internal pressure inside the spherical shape. Okay. This stress, sigma, in all direction, doesn't matter which direction you cut the spherical shape, is the same. And we call it circumferential stress or tangential stress or hoop stress. The best name for that is hoop stress, sigma h. Then we are going to calculate sigma h. Sigma h apply at this edge, this area of the metal. Then the length is equal to 2 pi rm times thickness is the area of the cut edge times sigma h is the force, internal force. It must be equal to the external force. External force is due to internal pressure. Internal pressure acts in all directions in this portion of the part, and then all directions except the longitudinal direction will neutralize each other. Pi times actually the resultant of pi in y direction or in other direction neutralize except resultant of pi times area, that is the projected area of these vessels, which is a complete full circle, PRM divided by 2 is the area. Then this area times PI is the external force applied because of internal pressure. Okay? Then sigma h is equal to, you can cancel out Rm here with 2, pi with this one, and then you have here 2t, and here is pi Rm divided by 2t. This is the hydraulic stress hoop stress or circumferential stress or tangential stress in pressure. This is the only stress that we have in spherical pressure vessels. And let's, in all direction, if you consider an element on the shell, in all direction, the shell is under tensile stress, sigma h. And this is the case that the Mohr circle convert to a point. If you draw Mohr circle for that, sigma 1 and sigma 2 or sigma x and sigma y has the same value. And there is no shear stress. We have only hoop stress, two hoop stress, sigma x and sigma y both in the same, or you can say sigma 1 and sigma 2. Principal stresses. Then hoop stress, in this case in two-dimensional, reduces to a point. What about the other stress, sigma z? We don't have sigma z, but it means that its value is 0. If you consider the 0 value for sigma 3 or sigma z, then we can draw a Mohr circle at this case. We can draw a Mohr circle at this case. And then Mohr circle here gives us a very valuable information. The point between these two, 0 and sigma h, I expected that it won't work. Okay, what does it mean for us? It means that in this case, we don't have tau max. And the student thinks that the tau max here for this case, because the Mohr circle is a point, is 0. Unfortunately not. This is tau max. This value is equal to half of the sigma. And in design, you must consider this shear stress in this design. Okay? Then that's a Mohr circle for a spherical shear stress, plane stress, and both stresses in x and y are equal in this case, and Mohr circle two-dimensional reduces to a point, but because there is another stress, sigma z, that apply in the z direction in the thickness of the shell, actually, but the value is 0, we must consider it, because the difference between them, 0 and maximum stress, produces a shear. It means that if you rotate it 45 degrees, what we have, original case of the element is sigma h and sigma h. When you rotate it in here, in Mohr circle, 90 degrees, and for the original element, how much? Actually, in this position, counterclockwise, then we have a state of stress here that is axial stress here is equal to sigma h over 2 here, here, here both are tensile. But there is a tau max, which is actually considered positive, which is we consider it as clockwise, which is equal to sigma h over 2 as well. That's the state of the stress inside the material, inside the thickness. If it rotated 45 degrees, we have another state of stress. We have a shear stress here in this case. Okay, that's everything about the pressure vessels. Let's have a look on ASME standards. ASME, we take this formula and consider the effect of corrosion, effect of welding, effect of milling machine to produce the plate, tolerance, milling machine tolerance, and then reach to a formula and calculate actually the thickness, because they know the material. Assume that our material is SA 5116 grade 70, for example, at 300 degrees centigrade temperature, is S allowable stress, which is the maximum working stress that can happen. We allow to happen. We are not allowed to go more than that. This stress here, for example, at 300 degrees is 128 megapascal. Okay? Then we do not need this state of stress anymore. ASME says that what thickness is required for a pressure vessel that wanted to work at 300 degrees centigrade, and for example, PI is assumed at 500 psi. For 500 psi, it is equivalent to, or not 500 psi, let's consider 500 psi is 3.45 megapascal. It's too much. They use it for tests also, maybe. Or 1.5 times 500 psi is 650 psi for tests sometimes. Sometimes they use 500 psi, sometimes they use the working pressures times maximum working pressures times 1.5 times. Okay, let's consider that we wanted to use it for PI is equal to 2.5 megapascal. The standard says what? Standard says that required thickness. Let's look at the code and see what's the difference between the standard formula and this one. The standard for spherical shape says that required thickness is equal to internal pressure times outer radius. Outer radius is the conservative sides of the formula. Why? Because the difference between when we consider outer radius or mean radius is less than 5%. It's not a considerable amount. Divide by what? Divide by 2, that is taken from here. If your thickness goes there and sigma comes here, 2 allowable stress, which is the role of the sigma. We assume that under this pressure, we reach to the maximum allowable stress. Sigma is S, allowable stress, times efficiency of the welding. Welding reduces the amount of allowable stress, make the plate weaker. And we must count out at a smaller than allowable stress that is given by the ASME, for example, section 2, division 1. On that, then sometimes if you test the welding, by X-ray, the full test means that the efficiency is 1. But is there you just test some spots, some points only, depends on the number of points. You can give it 0.85, 0.80, and this is less than 1 if you are not sure about your X-ray. If it totally fully radiograph, then efficiency is 1 plus 0.8 times internal pressure. Again, this is the standard. This doesn't add a valuable, considerable value actually, because For example, here, which is 2.5, is added just 2. Okay? Let's consider the thickness, required thickness. For this case, is 2.5 times, assume the O is equal to 1800 mm. Then this is 900 divided by 2 times 128 times 1 plus 0.8 times 2.5. Then this is actually, if you consider that, we reach to 128 times 2 plus 2 here is 258. And here is 2.5 times 900 is 2250. And the thickness is equated as 8.72. Okay. Is it enough? No. Nominal thickness. You must calculate nominal thickness according to a standard, which is the required thickness plus mechanical allowance plus corrosion allowance plus erosion allowance plus milling tolerance, mill tolerance. But not all products is subjected to all these allowance and tolerance. Not all of them. But one thing I'm sure is they consider the corrosion allowance. Actually, it's something like 3 millimeters. Sometimes erosion happens, they have to add it to the thickness, sometimes not. You must, depends on the material that is actually take in the pressure vessels. Milling, actually, they put 12.5% for milling tolerance. It means that if you go to the market and ask for a 20, nominal size 20 plate of this specification, when you measure it, it is 12, maybe 12.5% less. It means that 20 nominal size, real size is 17.5, 12.5% less. This is why you must consider it. You cannot go to the market and say that, okay, I need just this size of plate. You cannot find it. You must go for what is available in the market. Then T required here is 8.72. Mechanical allowance depends on how much you must add to here. For what? After fabrication of the vessels, maybe you wanted to remove some materials from the shells. You must actually predict this part of the production as well, that you need to remove some material. Then you have to add it first, and after production, you can remove that. But here, we don't consider it as well, but 3 for corrosion, for allowance, nothing for this 12%. Then standard says that nominal T, required T 8.72 plus corrosion allowance divided by this mill tolerance, that is 1 minus 0.175, and is equivalent to the thickness that we get here is 11.72 divided by 0.875, 30.39. Do we have this plate in the market? No. We must go to find out nominal size plates in the market with this specification, maybe 15. Maybe 15. And if you, let's multiply 15 by 0.125 minus 15, it is 30.12. standard value that we have here. Maybe you go to the above actually size more than 15 or 16. It depends on the manufacturer and standards that what is recommended actually. But the code for production is here. If you added mechanical allowance, if you added erosion allowance, then the thickness will be larger and you need the larger plate. It depends on conditions. What is the material inside the tank? Is it a corrosive material? If the material is flowing inside the tank, in this case, it has a solid particles that attack to the internal surfaces of that produces wear due to erosion. All of them must be considered during the life of the pressure vessel. Okay, thank you for watching. See you in the next video.